Hello, this video is measures of central tendency. And we're going to start out by talking about the main three here, mean, median, and mode. So let's see what that's all about. Mean is just essentially the arithmetic average. Now we're going to see a couple different types of mean coming up, but just your general mean will be taking a set of numbers, adding them up, and dividing by how many numbers you have. Now let's get used to some symbols here that we're going to use throughout the course, and these come off that basic terms and definition sheet that I have. If we're talking about population, meaning the data is defined to be a population, the population mean, we use a Greek symbol. In fact, with a lot of population parameters, you're going to see Greek symbols here. It's this funny looking U here. It looks kind of like an M, kind of like a U, but it's actually the Greek letter mu. This has a longer tail there on the left side. And this little Greek symbol, you don't have to know this symbol, the sigma, the capital sigma, don't worry about that. But anytime you see that in front of a variable in math, that means adding numbers up. So that means you're going to add some stuff up. All right, so this just means add them up and then divide by n, where capital N here is the population size. So that's real easy. Now, anytime we're talking about a sample, this is the notation that we'll run across. It's a little x with a line across of it, and we just call that x bar. So anytime we see x bar, that represents the sample mean. Once again, you're adding the x's, and you're still dividing by a sample size, but they use lowercase n for sample mean. But you're still adding them up and dividing by how many you have. For the different n's, there is a situation that we're not covering in this class, but there is a situation where both capital N and lower n would be used in the same formula, so there needs to be a distinction between the two. But just essentially, the simplest way to think of it is how many numbers do you have. All right, so find the sample mean for this data. All right. 3, 11, 4, 9, and 16. Now, because it said sample mean, I'm using the notation for sample mean. Well, all I'm doing is adding those 5 numbers up and dividing by 5. Notice how I put parentheses around this. I'll see people improperly use calculators and get the wrong answer, and that gets good information to know as we go throughout this course. There's going to be other situations where we're subtracting stuff in a numerator, and then we're dividing by the denominator. But if you just went without parentheses, if you just went 3 plus 11 plus 4 plus 9 plus 16, then divided by 5 with no parentheses, you would not get the right answer. Now, you could hit enter after you add those 5 numbers up, enter, and then divide by 5. That would be correct. Well, anyway, we get 8.6 for that answer. Next one, population mean. So that we're determining whatever this data is going to represent a population for whatever reason. A population that only has 5 values. That's okay. Populations are usually larger than that, but that's okay for this exercise. Well, now I'm just using that Greek letter mu. Adding the 5 numbers up, dividing by 5, we'll get 8.8. So you can see the calculation's done exactly the same either way. Now let's talk about something called another measure of central tendency called the median. Now the median essentially is the middle value, which sometimes it may not be the value that's actually in the data set, which you'll see shortly, but sorted in ascending order. So it's very important here. So what the median is saying is that 50% of your values are less than the median and 50% are greater than the median. So unlike the mean, where you take 5 numbers and add them up, the order would not matter. And the addition property is commutative, meaning you can change the order. But this is a little bit different. This is more of a measure of ranking, so you would have to have them in order. So let's say we have these numbers. I won't read them all out. You can look right at them, but I'll just move the bouncing ball across all of them. Find the median. So I need to sort and get them sorted lowest to highest. And then look in there, and 9's right in the middle. So 9 is telling me that half the number, so there's 4 numbers below 9, there's 4 numbers above 9. So the median would be 9. Now, here's another example. And you might be thinking, hey there, what if we don't have, one exact value that fits in the middle? Well, very good, because that's what's going to happen right here. When you have an even number of values. When you have an even number of values, you still sort them and put them in order. But you see, if you went through this list of these numbers, and you would not find one single number in the middle. There's not. To where you have, half the numbers on one side and half the numbers on the other. So what you do in this case is you average the middle too. So it's very possible the median may not even be a number that's in your list. So let's see what happens. So you see that 9, and as I circle these numbers, I can check real quick if there's 4 to the left, 4 to the right. So you average the middle two. You just take the average of the two that you find right there. So 9 plus 11 divided by 2 would equal 10. Here's a little block if you want to do this in the TI-83, 84, Inspire, whatever kind of, or other calculators can possibly do it too. I just don't know the commands as well for those. I'd probably have to look up a YouTube video if you came to ask me about another one. But anyway, if you hit the stat button and you go edit, it's going to bring up a list of numbers, or a different list. So if you use L1, and for the calculator, let me mention that you do not have to put them in order. You only have to put them in order if you're doing it this manual way up here. So I entered the numbers in as they were given right up here. So there's, let me just zoom in this a little bit for a second. 3, 11, 2, so forth, blah, 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 all the way to 18. So at that point, when I enter my numbers, I usually go second, quit, and that gets me back to the home screen. Then I go back to stat again. Then I go calc. I go 1var stats. Now this is maybe a little bit, when you hit 1var stats, and I can't remember in the newer calculators, it might be a little bit different, but anyway, it might ask you for which list it's in, which ours is in L1. This TI-84 I used here, if you don't have to put a list in there, if it's in L1, that's the default. So if you just hit enter, it'll spit out everything. But some of the newer ones might actually want you to tell it the list. Now, of course, it may bring up L1 as the default. I'd have to look and see. But my point being is here, well, let's say if your data was in L2, that's why I try to always use L1. I would have to go to the calculator screen, and here we go. To bring up. There's some calculus. That looks like fun, doesn't it? Do I have anything in a list here? So I don't want to make this too time consuming. Oh, okay, there's a list. So I go stat, edit. Oh, that's something. Dang it. Stat, calc, 1var stats. Yeah, okay. Now, if it brings up this one, a little bit newer operating system, you see it's default to L1. I don't think you have to put anything in that frequency list. And you hit enter. And see up here, it just shows, it's just using the X bar notation, sample mean. But we've already talked about that would be the same as population. Well, there it is. There's the median right there, 576. So in this particular operating system, slightly older, just it doesn't bring up that you hit enter and L1 is the default. If it was a different list, you'd have to tell it like L2 or whatever. Oh, that's what I was going to show you. Choosing a different list. When you got to that screen where it's asking for the list and you choose a different list, it's a second font. There's the alpha is a green one here, and the blue second. So it'd be second number 2, and that brings you up L2. That's how you would tell it was in L2. I try to use L1 as much as possible. There'll be some scenarios later where we'll be using both L1 and L2 simultaneously, so that'll be different. But if it's just one set of numbers, L1s, just stay that way. You can just leave that as a default, and you're good to go. And here it is. So there's our median right there that I got right here. 10 right there. Okay. So whatever you want. That's what I'm saying. This class, as long as you have at least the basics, got to be like a scientific calculator. It can't be something that just came out of a box of Cracker Jacks and it can only do add, subtract, divide, multiply. It's got to at least have square root. Even a $10 TI-30 would be acceptable. But if you have access to this calculator, maybe you already have one or a friend has one they don't need, it can save you a little time on some of the calculations. Now in another video, I just redefining this again, but I mentioned when I was doing dot plots on the stem and leaf display, talked about the idea of an outlier. Now let's say, what if we had an exam with the following results, where the mean, the class average was 78, but the median was 84. That means half the people did better than 84, half did lower. What would this tell you? And this is sort of like if you're looking at it as an instructor point of view or whatever, trying to determine, well, how'd this test turn out? When you're trying to design a fair exam, that sort of thing. That tells you that there would be some significantly low scores that would weigh the mean down versus the median being 84. And that's something to consider. If an instructor gave an exam, let's say half the class did better than 84, that probably means that the test, certainly was not unfairly hard. But if you had people in there making like 10s and 5s and 10s and 20s and that kind of thing, that would just tell me, it wouldn't tell me that the person was stupid or anything. It would just tell me they were completely unprepared. That would be the most likely scenario. They walked in, they weren't prepared for the exam, so they did poorly. That does not mean the exam was too hard if you're not prepared. So this is where the median, you might look at that, the instructor might say, well, half made better than 84. I think this test is okay. In other words, I'm not concerned about the people that made 10s, because like I said, they probably just weren't prepared. And here's a very important statement right here that we'll keep in mind. Obviously, this will stay in the notes here, but the median is unaffected by outliers. Some other things we're going to learn are all affected. See, the mean would be affected by an outlier. Let's see, do I have an example of that written down here? Well, I don't, but I'll just say it verbally. And it should be easy for you to understand if I just say it verbally. Like if you had the data set 1, 2, 3, 4, 5. That's pretty simple. Median would be 3. And then suppose you had another data set, 1, 2, 3, 4, and then 500 was the fifth number. The median would still be 3, but the mean would be completely different than the first mean would have been 3 also. But this new mean would be over 100. So you see, there's certain types of situations where people would prefer the median as a measure versus mean. So people are kind of free to choose whichever they think's best for the given situation. I mean, if you're looking at data in the sort of real world there, but So if you didn't want outliers to affect your results, you would want to use the median. Okay, so this is just outlier. I'd said this in another video. Far removed from the other entries in the data set. Okay. And so here's a set of, so here's sort of the exam score thing I was talking about too. So you see how I put an intentionally low score in there? Two low scores, in fact, a 10 and a 20. We would consider those to be outliers. And we'll sort of have more ways to talk about what really makes something an outlier, mathematically. Right now, that's okay. Just kind of just be aware of the idea of an outlier, and then we'll worry about maybe specifics a little bit later. So you see with this data set, with these exam scores, the mean was 74 because those two real low scores, but the median would be that because there's 10 numbers here. So when you have an even number of numbers, you'll have to average the middle two. Sometimes it might be the same number. So if it was 85 and 85, the mean would be 85. So you add that. So the median is 87.5. So that tells me half the group did better than 87.5, half did lower, but the mean is just strictly weighted down by those two outlier scores. So same thing here where the mean has an effect, that outlier affects the mean, but would have no effect on the median whatsoever. Mode. Mode is a data entry or entries that occurs with the greatest frequency provided it occurs at least twice. This is the only one of these three measures of central tendency that we can use for qualitative data. The other ones, the first two obviously have to be numerical. They have to be numbers. But this could be numbers or any kind of qualitative data. Let me bring up that example so I can show what we're talking about here. Let's see. Oh, went too far there. Oh, that's that. No. Okay, where's that? Let's see. Yeah, this one. Mode is the value that's chosen that occurs the most, provided it occurs at least twice. So you can have qualitative or quantitative data here. So for this one, the mode would be Honda, because there were more choices of Honda than anything else. All right. Yeah, so that's all you have to do there. Now, I've seen problems like on the final where they actually list a few word terms out. And so you would just, count the word that appeared the most. Or the word that you counted the most time. There we go. Now here's a data set. These have 6 different numbers. So since nothing repeats, no mode. Now sometimes people kind of overthink this. They make it more difficult than need be. They kind of misunderstand what I'm saying, and they'll think that anything occurs more than once as the mode. That's not true. It just means it has a chance to be the mode. So here we have 1, 1, 2 ones, so that means it has a chance. 6 has a chance because it occurs more than once. But then 7, there's 2 of those, but 7, there's 1, 2, 3, 4. 4 7s. So it wins the mode competition because there's more 7s than anything else. So keep in mind that the answer here yeah, not how many of them there are, it's the actual. So whether that was 4 words or 4 numbers, it occurred the most times. So that whatever that is the mode. So it would have been, or it could have been a word. That would have been the mode. The word would have been the mode. Down here, now you can have ties though. Here we have 3 4s, 1, 2, 3, and we have 3 5s, 1, 2, 3. 2 modes, they tie, 4 and 5. So we would include those because they do tie there. Now we're going to start looking at all right, now we have something called the weighted mean. It's a specialized type of mean where it's different than just taking your standard mean and adding up the numbers and dividing. And this is used when we're deciding that particular values are kind of worth different amounts. They're not all equally weighted. And the easiest way, I guess, for a student to relate to this is if you're taking some sort of course, even like this one, where different scores have different amount weights. So you see that's all values are not equal, in other words. So here, this particular example, we have a homework grade that's 15%. Quizzes is 15%, computer labs 10%, midterm exams 30%, final exams 30%. Now don't let this formula scare you up here. It's real easy to use. They're using the population mean because there's no way that this is a sample. This is obviously using all the values. You take X, each particular score that relates to that, and then you multiply it by the weight, and then you divide it by the sum of the weights. Now in this particular example, the sum of the weights will be 1 because they add up to 100%. So all we have to do is go score times weight plus score times weight, converted from percentage to decimal. Score times weight, so forth, and add them up. So it's really not too bad. So let's say our scores, according to this, in order, respectively, 92, 80, 100, 75, 76. So we made a 92 on the homework, 80 on the quizzes, 100 on the computer lab, 75 on the midterm, and 76 on the final. So we're going to see what our average is. I'd say in a normal, if they were equally weighted, we would just add them up and divide by 5. But that would not be correct for this formula. That's all we do. So you don't have to line them up like this in a fancy chart if you don't want to. I just did that to kind of organize them, but that's not required. So however you want to do this. So basically you're going 92 times 0.15, 80 times 0.15, 100 times 0.1, 75 times 0.3, 76 times 0.3, and then adding that up. Now, I like to do it this way, but it's not mandatory. If you like to do each individual calculation and add them up, that just depends on you. But I like to just list them out, and I like to do them all in one string in the calculator, so I don't have to mess with. But if some people might want to have each individual calculation, that's fine, because all we really need is the total, the sum. So you see, I just went 92 times 0.15 plus 80 times 0.15 and put them in all one nice order. 81.1, and we would divide by 1, like I said a couple minutes ago, about the percentage adding up to 100. So the sum of the weights, well, you can add them up as decimal right there. You'll see it equals 1. So that means our course average is 81.1. So we did squeak out a B. Good for us. Now I'm just showing you what if the scores would have been equally weighted, just, all of them 20% each. And we didn't have to use a weighted mean, just showing you that. So here they are, add them up, then your average would have been 84.6. Now here's a classic question I get all the time, but I shouldn't have to answer this for a stat student, but at the end of the semester, I usually don't answer it anyway. I just tell people it's not hard to figure out, but what do I need to make on this grade, this score to make a certain score for the course? And solve that yourself. You don't need me. All right. Just sort of set it up as a simple algebraic equation. See, let algebra be our friend here. So we're saying we haven't. So we haven't using the same scores except for the final. We're saying what do we need to have an 80 average, and that obviously that's the minimum. So we're saying 80 or higher, whatever. What's the minimum score to have an 80? So all we do is sort of take that same equation, except this time we're trying to get it to add up to 80. We know the right side this time, and we just let that be some variable like x is fine, and that's what we're solving for algebraically, and we just solve the rest of that. And let's see. Yeah, so you just kind of solve that algebraically. I'm just trying to see if I can make some room here for this, but I'm going to anyway. And actually, I'll put it right over here. So 72.333. So let's say that we can't make a 72. Can't make that score. So, well, obviously, if the instructor, usually can't speak for all of them, but I would think a 72 would get you close enough to, 79 point something, whatever, where that would be considered an 80. But if you want to be technical, it would take a 73 then to get you literally slightly above 80. But I would think 72 would get the job done. And let's see, this one, I wouldn't worry too much about this one, but it's, if you were calculating GPA, I like to use the weighted mean example more than I do this one. So let's say, 4, 3, 2, 1, your standard GPA scale. This one would be, you divide the total number of grade points, which grade point would be hour taken times point value for the course. So like a 3-hour A would relate to 12 grade points. Then you divide it by the number of the weights, which is the hours taken. So you divide it by the hours taken. So it's grade point over hours taken. So with that one, if you have a ACBA, well, I should have probably changed this and put a 4-hour course in there to make it a little more interesting. But because since they're all equally weighted, I guess all you have to do is add up 4, 2, 3, 4, and average those numbers up, and that would do it. But anyway, but that's why if they weren't equally weighted, if you had a 4-hour science class and stuff like that, you would need to use this method to do it. So you got 12 grade points for the stats, 6 for the accounting, 3 times 3 is 9 for management, 3 times 4 is 12 for the marketing. Adds up to 39. 39 divided by 12 is 3.25. Now let's look at an example. Now you can really handle this by either the weighted mean method, sort of, or you can do it another way, which I'll say, which will be a lot longer and a lot worse. So this frequency distribution shows demands laptops, computers sold by Costco in the last 50 days. Determine the average number of laptops sold per day. Now, this is saying, okay, 0 laptops were sold on 14 days, and then 1 was sold on 8 days, 2 were sold on 8 days, 3 were sold on 12 days, 4 on 5 days, and 5 on 3 days. Now, one way, which would be the long way, and I wouldn't recommend doing this, is, you could literally list out 14 zeros, 8 ones in a row, 8 2s in a row, 12 3s, 5 4s, 3 5s, add them up and divide by 50. But, repetitive addition is the same as multiplication. In other words, if you have 5 times 5 times 5, 5 plus 5 plus 5, that's the same as saying just 3 times 5. And that's what we would do here. I don't have this written out. I may do that later, but you could so we're going to be dividing by 50 because that's the total of the frequencies. I mean, it tells me in the problem, but I could have added that up and got the 50. So essentially it's 14 times 0 plus 8 times 1, so it's going to be 8 plus 16 plus 36, 12 times 3, plus 20, plus 4 times 5, and then 5 times 3 is 15. Yeah, I'm not using a stylus and a tablet PC. I'm just having to use a regular mouse here, so that's why it looks so bad. 24, 60, 80, 95. So I get 95 divided by 50. So they were selling an average of 1.9 computers per day. Okay, I paused the video for a moment because I went and did something in the calculator just to save some time. So let me show you what I did. You can actually do this also in the calculator by using this technique, which actually is going to be calculating it the way I just did it. So you go into stat, so I've already done this, stat, edit, and you can see I used L1 to list all those computers sold 0, 1, 2, 3, 4, 5, and they have to be done in correct order here. And then L2 represents the number of days that were sold, 14,888,80. So you can see that matches this right here. So if you do that, like I did here, and then quit out of that, go stat, calc. Now, the earlier example we did of just, for the median, and this also works for the mean and median, that 1 bar stats. This frequency list was left blank, and that's the way you want to do it, just L1. But for this particular exercise, we put L1 in there for the list, and the frequency list we put in as L2. So we have that there, and of course, make sure you want to get rid of that L2 whenever you're not doing what I'm doing right now. Go back to leaving it blank, and you go calculate, and then the mean right up there at the top was 1.9, even though I erased it here, but you saw me go, when I went 95 divided by 90, that 95 divided by 50, that gave me the 1.9. I think I'm going to copy these screenshots in here. Probably go back and add the manual work later too, but I'm not going to revise the video for that, but let me just get these in here now and I'll deal with that after the video. But let me go back to the screen with the list. There we go. Get rid of that. So I go, and let's put that over here. Then I'll deal with that later, but 1.9, that's there, so all right. So we can move on there. So now let's talk about different types of shapes of distributions. We have one called uniform. Now, uniform means the heights are roughly the same. Now, if you're saying something is perfectly uniform, then they would have to all be exactly the same, meaning every frequency would be exactly the same number to be perfectly uniform. But if we're just sort of saying a general form of uniform, they're all kind of roughly the same, and the mean and median should be very close to each other in value. So let's say, and I'll just sort of read these out. Let's say I'm just reading out frequencies, not the x values. That doesn't matter in this case. Well, let's say the frequencies were going like 6, 5, 6, 7, 6, 5, 6, 6, 6, 5. You can see those are all kind of close. They're not too extreme. So we would probably consider that to be uniform. Now, the next one's called symmetric. Now, I'm saying symmetric but not uniform because technically all uniforms are also symmetric, but not all symmetrics are uniform. So that's why I'm just saying symmetrics that are not uniform. Meaning, it doesn't have to always look like this particular shape, but this is an example. Any graph, if you kind of folded it across the middle, and it looks like it would be roughly the same on both sides. And this is another one where the mean and median would be close to each other in value. But that's where you'd be looking at, the frequencies symmetric on each side would be about the same, and then it wouldn't really matter. In fact, you could have this histogram could have the bars sticking up. Let me find it. Yeah, there's lots of ways to make a histogram. I mean, let's just say, and this is probably going to look terrible, but that's all right. Yeah, it could be something even like this. That's getting worse, isn't it? All right, come over here. Yeah, so we're not saying it always has to be the highest in the middle, but yeah, you see, I'm just kind of draw a little line right here, but if I folded that over, it'd roughly be the same on both sides. That's essentially what symmetric is. Now we have two types of graphs that are called skewed. This might kind of seem backwards logically to you. I saw something in the book that kind of an interesting way to show it. I don't know, it's not that big a deal, but skewed left means that graph will show more data on the right side, the upper end, than it will the lower end. And with this, the median would be a number that's larger than the mean. So I know it probably seems backwards, but at least it's backwards for the other one also, because that, heavier to the right might make you think that would be skewed right, but it's just the opposite. It's heavier to the right means skewed left, and the cute little quip that the book said there was, imagine if you were skiing down off the top of this slope, you would be skiing to the left. So I don't know if that helps or not, but I thought that was kind of an interesting way to say it. You ski left, so therefore it's skewed left. Just like here, heavier data is on the left side, the lower end, that's actually skewed right, because you'd ski right. So this case, the median is a bigger number than the mean, so median is smaller than the mean. But for skewed left, the median's a larger number. Skewed right, the mean will be a larger number. And probably significantly larger. I'm not talking about if the mean was 20.2 and the median was 20. I would not consider that to be skewed right, because that would almost be, one of these two up here. They don't be exactly the same, very close. But I would say if the data had a mean of 20 and a median of 25, then we're possibly, getting somewhere as far as the possibility of it being skewed left. There needs to be a significant difference, not an exact. I know this makes it sound like exactly, but as far as any purposes, if that comes up as a homework question or something, just do whatever this says. If it says it would probably, if the problem said the median was 20 and the mean was 20.2, you probably should answer it like that, even though I don't necessarily wholeheartedly go along with that. But all right, here's something I snipped out of the book there that you can read if you'd like. Just kind of gives you some advantages and disadvantages of mean, median, and mode. I'm not going to read all these out. I'll let you read these yourself. So, and right, that's going to conclude this video.